This is Chapter 19, Module 4, White Blood Cells, Platelets, and Hemostasis. The learning objectives of this module are 1. Categorize white blood cell types based on their structures and functions, 2. Describe the structure, function, and production of platelets, and 3. Discuss the mechanisms that control blood loss after an injury and describe the process of blood clotting. White blood cells, also called leukocytes, are formed elements that help to defend against pathogens and remove toxins and wastes from the blood. These specialized cells do not have hemoglobin as the red blood cells do, and so they do not function to carry gases. They also do not have nuclei and other organs, so they are not able to produce proteins to repair themselves. White blood cells are mostly found in connective tissue proper and lymphatic system organs. Only a small number of white blood cells are found in the blood. There are several different types of white blood cells, but all of them have a few basic characteristics. They can all migrate out of the bloodstream to other tissues. They all have amoeboid movement and are able to move through the tissues. They are attracted to chemical stimuli, a characteristic called chemotaxis, which helps them to find pathogens and toxins. In addition, some of the white blood cells are phagocytic, meaning they will engulf pathogens and wastes. There are 5 different types of white blood cells: neutrophils, eosinophils, basophils, monocytes, and lymphocytes. Neutrophils make up 50 to 70% of circulating white blood cells, meaning they comprise 50 to 70% of all the white blood cells in blood. Their cytoplasm contains lysosomal enzymes and bacteriocides, both of which are toxic to pathogens. Neutrophils are very active and very fast, the first cells to attack bacteria. Neutrophils are phagocytes and will engulf and digest pathogens. Eosinophils make up 2 to 4% of circulating white blood cells. Eosinophils attack large parasites and excrete toxic compounds to kill them. Eosinophils are phagocytic and will engulf these pathogens. Eosinophils are sensitive to allergens, and that means when a person is having an allergic reaction to something, the percentage of eosinophils in the blood will increase. This is a good diagnostic tool when running blood samples to see if an allergic reaction is occurring. Eosinophils also help to control inflammation with cytotoxic enzymes that they produce that help to counteract the inflammatory reaction of the body. Basophils make up less than 1% of circulating white blood cells. Basophils will accumulate in damaged tissue and release a chemical called histamine, which dilates blood vessels, as well as heparin, which prevents blood clotting. Monocytes make up 2 to 8% of circulating white blood cells Monocytes have a large and spherical appearance and make up 2 to 8% of circulating white blood cells. They leave the blood by squeezing between the endothelial cells lining the blood vessels and enter the peripheral tissues where they become macrophages. These macrophages are phagocytic and engulf large particles and pathogens. They secrete substances that attract other cells from the immune system, as well as fibrocytes to areas that have been injured. Lymphocytes make up 20 to 30% of circulating white blood cells. They are larger than the red blood cells. Lymphocytes migrate in and out of blood. They are mostly found in connective tissues and lymphoid organs. These highly active cells are part of the body's specific defense system. There are 3 classes of lymphocytes: T cells, B cells, and natural killer cells. T cells attack foreign cells directly. B cells differentiate into plasma cells that can synthesize antibodies. Antibodies attach to pathogens to help destroy them. And natural killer cells detect and destroy abnormal tissue cells, such as cancer. The number of white blood cells can be measured in a blood sample to detect changes in the white blood cell populations. Infections, inflammation, and allergic reactions can all change the percentage of white blood cells in a sample of blood called a differential blood cell count. For example, leukopenia is a term given to an abnormally low white blood cell count. And leukemia is a term used when there is an extremely high white blood cell count. Lymphocytes are produced by myeloid stem cells during the process of lymphopoiesis. The production of all white blood cells is called leukopoiesis. White blood cells all develop in the bone marrow except for the monocytes, which develop into macrophages in the peripheral tissues. Platelets are fragments of the megakaryocyte cell and are involved in blood clotting in humans. They circulate for 9 to 12 days in the blood and then are removed by the spleen. Most of the platelets are reserved for emergencies. In a normal blood sample, the platelet count should be 150,000 to 500,000. A number below this suggests thrombocytopenia, or an abnormally low platelet count. A number above this suggests thrombocytosis, or an abnormally high platelet count. Platelets release chemicals used for blood clotting, so they can temporarily patch damaged vessel walls and reduce the size of a break in a vessel wall. Producing platelets is called thrombocytopoiesis, and this occurs in the bone marrow as well. Large cells called megakaryocytes in the bone marrow have pieces of cytoplasm and membrane that pinch off to create the cell fragments that are called platelets. When damage occurs to a blood vessel, the platelets help to stop the bleeding. Hemostasis is the term given to the cessation of bleeding. Hemostasis occurs in 3 phases: the vascular phase, the platelet phase, and the coagulation phase. The vascular phase occurs immediately after a cut through a blood vessel. This phase lasts 30 minutes. During this phase, the endothelial cells of the blood vessels contract and release chemicals that cause vascular spasm and narrowing the lumen where the cut occurred. The plasma membranes of the exposed endothelial cells become sticky and adhere to platelets and to each other. The third and final stage is called the coagulation phase that begins 30 seconds or more after the injury. During this phase, the circulating plasma proteins called fibrinogen convert to an insoluble fibrin. The fibrin get trapped in the platelet plug and form a fibrin network. The fibrin network grows as more and more fibrin become trapped and tangled in the platelet plug until a blood clot is formed that seals off the damaged portion of the vessel. Calcium ions and vitamin K are both essential to the clotting process. Eventually, the platelets begin to contract, causing the torn edges of the vessel to be pulled closer together, reducing residual bleeding and stabilizing the injury site, making it easier for fibrocytes, smooth muscle cells, and endothelial cells to complete repairs. Slowly, the clot will begin to dissolve and the fibrin strands will be digested and the clot disappears. This ends Chapter 19, Module 4, White Blood Cells, Platelets, and Hemostasis.